In our approach, we differentiate three parts: the sender of the data, the server where the data is temporarily stored, and the receiver of the data. Our sender program, written in Java, has to solve the most tasks. At first, a selected file must be encrypted because we don't want to show our file exchanges to everyone. For this, we used the Bouncy Castle API, especially as provider for our AES cipher. In addition, a unique ID, this is our special mark, must be generated. This should work as our marker. And in the next step, the file gets split into parts, like I guess it was in the animation before. It's split into parts which are adjusted to the size of the payload of one DVB packet, 1,360 bytes. Into the first 32 bytes of each part comes the ID, followed by the part number. After that, data and ID are sent. After that, the data and the ID are sent via HTTP to our server. If wanted, this connection can also be secured, for example, with an anonymous proxy service. To send the files via HTTP, we use the W3C's JWPut class that belongs to the mentioned WinIE Network Utility API. But that is not all our sender program has to do. It also has to export the key phrase into a key store file. The same applies to the ID, which is saved together with the original file name and the number of parts of the file was split into. These two exports are necessary for everyone who wants to receive, join, and decrypt our file. At this current moment, there's no key management implemented yet, so the key has to be sent perhaps via email to the wanted receivers or must be exchanged during an evening at the pub, for example, or I don't know. Now, let's take a short closer look at the server. Our server bases on the W3C's Jigsaw web server. At first, it stores incoming files and manages the appended IDs. So when there is a file request mostly from an ISP, the server is able to mark our file's HTTP header with our associated ID. That's all our server has got to do, so it's not that much as the sender has to do. Last but not least, we've got our receiver, and here it was a little bit more complicated because Java doesn't get the possibility to access a hardware device directly. So we used the JPCAP class package that makes use of the libpcap and the raw socket API, and together with the Java native interface, we could access the C code of the libpcap and so access our wanted network device, the DVB-S card. So, in simple words, after this implementation, we were able to listen on the satellite broadcast in promiscuous mode. And we were able to search for or to filter for our wanted ID. The wanted ID is imported from the emailed or another way delivered ID file. If a packet with our ID is found, it is automatically written on disk, and after the part is stored, the program compares the number of saved file parts with the number of total file parts, which is also told by the imported ID file. And when all packets are received, the parts can be joined together and the file or the files can be decrypted with using the also imported key store file. So at first, how we want to extend or what were our first problems or what are possible problems and what were the ways we tried to find solutions. The first problem we found was that there could be a possibly high error rate. That means that some parts get lost, or are damaged, so that the receiver cannot join the files together. When this would happen to a normal receiver or an official client of the ISP, like our sender, then he simply would re-request the missing packages at his ISP, and they would be sent through his return line. But our anonymous receivers don't have a uplink connection to the ISP, so they cannot report a lost or a damaged file part. To prevent this, it is advisable to control the whole transmission also by the sender. So when he doesn't get all packets or he receives damaged file parts, then he could re-request them, but not as an error. He just re-requests the whole file part, so it's not sent through the terrestrial return line. To detect these defect file parts, we try to use, for example, a CSC method. Additionally, the request could be done automatically several times, because the possibility of one and the same data packet getting lost several times or multiple times is rather low. But we also should not forget that, especially in case of satellite broadcasts, interferences can have very local origins, like clouds, thunderstorms or so. From a little futuristic point of view, you could also implement methods to check the actual weather dates at the receiver's position and estimate his specific packet loss rate or so. So you can do if you want. But another real problem, so the high error rate was in our test wasn't a real problem anymore. Another problem could be the linkability. So this was in our first test. So users could try to reuse old IDs to capture new transmissions which are not addressed to them by our sender. To prevent this, we generate, as mentioned before, a long unique ID, 16 bytes long, for every single file exchange. So it's very improbable to have success by listening with an old ID. A little bit more complicated could be a provider-side encryption. In this case, our sender would use a proxy-like software provided from his ISP, and inside this piece of software is the decryption key for this user. And every time the user requests some data, it is encrypted by his ISP. The only suitable solution for us would be to extract the decryption key out of the provider's software and to share it with the receivers, which should be possible because the decryption key is in the software at the user's PC and it's not changing very often. Another another interesting point would be the anonymity of senders, or to improve the whole anonymity. Therefore, we need multiple senders who upload different files to our file server. After that, they do not request a special file, but a random one. This could also be realized server-side by sending a random packet on a specific request. If someone uninvited would be listening on the whole broadcast, he would try to join the packets of one specific user, but these packets would not all belong together because their common bond does not based on the user's MAC address as normal, but on our ID hidden in the file header. To illustrate this scenario, we've got the same components with additionally two other video file parts or other file parts on the server. Our holiday video is again split in parts, into 4 parts, I guess. Yes, into parts. And it is again sent to the server. After that, the sender requests some common packets which are rerouted as before from his ISP to the server. The other things are also at first the same. But now our receiver sees only the file parts of the correct video. He doesn't see the red ones because his part of software is filtering for the correct ID, unconcerned of the destination MAC address, which is normally important for identifying your files in the broadcast stream. But if there would be now someone else listening, he would, for example, see there are 4 packets delivered to our sender. He doesn't know anything about the real receivers. But these 4 packets with our sender's MAC address are not the correct parts of our holiday movies. There are, for example, 2 parts of the red file and 2 parts of the real movie. So he would only see some garbage data he couldn't join or even decrypt. So what are the next steps we want to take? At first, we're going to implement some methods for better analysis. That means, for example, a visualization of the file parts you're missing, or a statistic of how many packets are received during the first pass of sending, how many packets need 2 passes or more passes, and how many packets get lost, and so on. Another important aspect will be the exchange of the key and the ID file, because it would be very nice to provide an integrated solution additionally to the one exporting the file and exchanging it in a pub, or I don't know where. Additionally, the graphical user interfaces must be extended, just as ways to improve the sender's anonymity should be implemented in a more full way. So far, I guess yes, that's all from my side.